So we're going to be talking about antimatter. And to you, antimatter might sound like science fiction. But what I want to get over to you in this talk is that antimatter is science fact.
That canister contains an extremely combustible substance called antimatter. We need to locate it immediately.
When Dan Brown's Angels and Demons hit the shelves, it didn't just introduce readers to a gripping new thriller. It also catapulted the concept of antimatter into the mainstream spotlight. Suddenly, a term that was once reserved for physics textbooks and scientific journals became a household word, sparking imaginations and igniting debates about the boundaries between science and fiction. In the novel, antimatter isn't just a scientific curiosity. It's the centerpiece of a high-stakes, globe-spanning thriller, a force so powerful that it could change the fate of the world in a single instant. The heart of the story revolves around a stolen canister of antimatter supposedly created at CERN, the world's largest particle physics laboratory. In Brown's tale, this canister is depicted as a portable battery-powered bomb, small enough to be carried by hand, yet powerful enough to threaten the very existence of Vatican City. The novel dramatically exaggerates antimatter's destructive potential, suggesting that even a minuscule amount could unleash an explosion far more devastating than any nuclear weapon ever created. This portrayal turns antimatter into a kind of ultimate doomsday device, a substance of almost mythical power. The suspense builds as the canister's digital countdown ticks away, and the threat of instant annihilation looms over the characters. This ticking clock transforms antimatter from a scientific concept into a symbol of ultimate suspense and danger. Brown's story masterfully blends real scientific ideas with dramatic fiction, making the narrative both thrilling and thought-provoking. Readers are drawn into a world where the lines between reality and imagination blur, and where science becomes the engine of suspense. But this dramatic depiction also raises important questions. Is antimatter truly as dangerous as the novel suggests? Could it really be weaponized so easily? Or is this just a flight of science fiction fancy? And what about the idea of producing and storing antimatter in a portable container? Is this something that's even remotely possible with today's technology, or is it pure imagination? The story's blend of fact and fiction sparks genuine curiosity, inspiring readers and viewers to dig deeper into the true nature of antimatter, how it's created, and what real scientists are actually doing with it in laboratories around the world. So let's take a closer look, separating the science from the storytelling, to uncover the real story behind antimatter, and find out just how much of Angels and Demons is rooted in reality and how much is pure page-turning fiction. Antimatter is matter's mirror image. Every particle, like electrons and protons, has an oppositely charged twin. Paul Dirac predicted antiparticles in 1928, and Carl Anderson confirmed the positron's existence in 1932. The most dramatic property: when matter and antimatter meet, they annihilate, converting their mass entirely into energy, E·mc2 in action. This process is far more efficient than any chemical or nuclear reaction, fueling the idea of antimatter as the ultimate energy source or weapon. But if matter and antimatter are created in pairs, why is the universe made almost entirely of matter? This imbalance is one of physics' greatest mysteries. The real science is even more fascinating than fiction. Let's see how antimatter is actually made. CERN, near Geneva, is the world's leading center for antimatter research. But reality is far less dramatic than fiction. Scientists create antimatter one particle at a time using high-energy collisions in massive accelerators. Antiprotons are produced by smashing protons into metal targets, then separated and slowed down using advanced machines like the antiproton decelerator. The quantities are minuscule. After decades, CERN has produced only nanograms, billionths of a gram of antimatter. The quarter-gram bomb in Angels and Demons is millions of times more than all the antimatter ever made. Even producing a microgram would take thousands of years and unimaginable energy. The reality, antimatter is incredibly rare, expensive, and difficult to handle. So could it ever be weaponized? In theory, matter-antimatter annihilation releases more energy per gram than any other process. 1 gram could rival a nuclear bomb, but producing antimatter is staggeringly inefficient. Making just 1 gram would require more energy than humanity can generate in years. Storing antimatter is even harder. It annihilates on contact with matter, so it must be suspended in perfect vacuum by powerful electromagnetic fields. Current storage devices are huge, power-hungry and delicate, not portable or practical. With today's technology, an antimatter bomb is pure science fiction. The challenges of production, storage and safety are insurmountable for now. The universe keeps its most powerful secrets well guarded. Let's compare movie magic to laboratory reality. The sleek antimatter canister in Angels and Demons is pure Hollywood, a gleaming palm-sized device that looks like it could power a spaceship or destroy a city with the flick of a switch. It's the kind of prop that instantly grabs your attention, designed for maximum suspense and visual impact. In the movie, it's a compact battery-powered device with a dramatic countdown, heightening the tension as the seconds tick away. But how close is this to reality? Real antimatter storage is a world apart. Scientists use penning traps, sophisticated devices that rely on powerful magnetic and electric fields to suspend tiny amounts of antimatter in a vacuum, preventing it from touching normal matter and annihilating. These are not small portable gadgets. Instead, they're large, complex machines that require strong magnetic fields, ultra-high vacuum and cryogenic cooling to function. The technology is so advanced that it fills entire rooms with intricate equipment. These traps fill entire lab rooms and need constant power. If the electricity goes out, the antimatter is lost in a flash, but not in a way that's dangerous to anyone nearby. There's nothing remotely like a portable gadget or a ticking bomb. The real devices are massive, delicate, and require a team of experts to operate. If a real trap failed, the tiny amount of antimatter would annihilate harmlessly, releasing energy equivalent to a few milligrams of matter, barely enough to warm a cup of coffee. The result? Only a minuscule amount of heat is produced, far less than what's needed to cause any real damage. The idea of a city-destroying explosion from a containment failure is pure fantasy, an invention for the big screen, not the laboratory. The reality is far less dramatic, with scientists working in calm, controlled environments, focused on precision and safety. Yet the technical achievement is no less impressive. The engineering required to trap and study antimatter is a marvel of modern science. The science behind antimatter storage is a triumph of engineering, representing decades of research, innovation, and international collaboration. It's not a recipe for disaster, but a testament to human ingenuity and our quest to understand the universe at its most fundamental level. So what is CERN really doing with antimatter? Let's take a closer look at the real science behind the headlines. CERN's mission is to unlock the secrets of the universe, not to build weapons. Founded in 1954, CERN stands as a beacon of peaceful scientific exploration, dedicated to expanding human knowledge rather than fueling conflict. Its sprawling campus, nestled on the border of Switzerland and France, is a hub where curiosity and collaboration thrive. The research at CERN is centered on fundamental physics, delving into the very building blocks of matter, the forces that govern their interactions, and the profound question of why the universe exists in its current form. Here, scientists use cutting-edge technology to probe the tiniest particles, seeking answers to questions that have fascinated humanity for centuries. One of the most intriguing mysteries is why our universe contains so much more matter than antimatter. If the Big Bang created equal amounts of both, why did matter win out, allowing stars, planets, and life itself to form? Experiments like Alpha and Aegis are at the forefront of this quest. By studying antihydrogen, an atom of antimatter, researchers hope to uncover subtle differences between matter and antimatter that could explain this cosmic imbalance. The Large Hadron Collider, the world's most powerful particle accelerator, smashes protons together at nearly the speed of light. These collisions recreate the extreme conditions that existed just moments after the Big Bang, offering a glimpse into the universe's earliest moments and the forces that shaped it. Discoveries like the Higgs boson have revolutionized our understanding of the universe, confirming theories that explain how particles acquire mass and opening new doors to unexplored realms of physics. CERN is a truly global collaboration, uniting thousands of scientists, engineers, and students from over 100 countries. They work side by side, sharing ideas and expertise, driven by a shared passion for discovery, not by any desire for destruction. The real drama at CERN is found in the relentless pursuit of knowledge, the excitement of unraveling nature's deepest secrets, and the thrill of scientific breakthroughs, not in secret plots or conspiracies. Antimatter research at CERN is about solving the universe's greatest mysteries, not about creating doomsday devices. Every experiment brings us closer to understanding the cosmos and our place within it. Antimatter isn't just a scientific curiosity, it's saving lives. Positrons, the antimatter twins of electrons, are used in PET scans, a vital medical imaging technology. Patients receive a tracer that emits positrons. When these meet electrons, they annihilate, producing gamma rays. Detectors capture these rays to create detailed images of the body, helping diagnose cancer and other diseases. The amounts of antimatter are tiny and perfectly safe. This is a real-world positive use of antimatter science. Sometimes the most fantastic ideas from physics find their way into everyday life. Angels and Demons blends real science with fiction, making Antimatter and CERN central to its plot. But the story takes huge liberties. The antimatter bomb, portable containment and ease of theft are all pure invention. In reality, producing and storing enough antimatter for a weapon is impossible with current technology. CERN's focus is research, not weapons. And its security is designed for safety, not for guarding superweapons. The energy and effects of antimatter are often exaggerated for dramatic effect. The story's power lies in its ability to inspire curiosity, not in its scientific accuracy. It's a thrilling narrative, but not a documentary. Understanding the real science makes the fiction even more enjoyable. Fiction like Angels and Demons sparks curiosity about science, but it's vital to know where fact ends and fantasy begins. Real scientific understanding lets us appreciate both the storyteller's craft and the wonders of the universe. Scientific literacy helps us separate plausible ideas from pure invention, especially in an age of information overload. The true story of antimatter research, international collaboration, painstaking experiments, and the quest for knowledge is just as compelling as any thriller. The universe's mysteries, from antimatter to dark energy, are stranger and more fascinating than fiction. Science fiction inspires, but real science expands our horizons and deepens our understanding. That's the story worth telling and exploring.